Alright, hi Calc class, working on 5.4 notes today. I think I fixed the formatting issue that we were having by as a PDF, so let's see if it works. First of all, go ahead and pause and see if you can answer number 1 and number 2 using the first derivative test to find local extrema and then using the second derivative test to find local extrema. Push pause, see if you can get those. And when I say get those, I meant get these, your answers. If you have questions, I'd be happy to talk about it with you on Monday. Number 1, your answer was none, and on number 2, the local maximum happened at -2, 19, and the local minimum was 1, -8. Remember, the maximum is the y value, the -2 is the where it happens. This is what we're doing today. Mainly optimization problems, which means finding the max and mins of different situations. These are the 6 steps that your book puts into place to solve these, and although I don't write down 1, 2, 3, 4, 5, 6 as I'm solving them, I'm kind of thinking through it this way, reading it, identifying information. Step 2, drawing a picture, if possible, labeling everything we know, trying to figure out from the problem the important stuff and the stuff that I need to put in terms of another variable, what I'm actually trying to maximize or minimize, and from there you can find your derivative to find your critical points, check your endpoints, see where stuff actually happens, and interpret the results. So these are the 6 steps the book uses. I don't specifically go through them, but I think they're helpful. Helpful for problems like this. A rectangle is to be inscribed under one arc of the sine curve. What is the largest area the rectangle can have, and what dimensions give that area? Alright, so what I'm talking about is, oops, forgot to push my pen, is this. Here is one arc of my sine curve, and here is a rectangle inscribed in it. So if this is my rectangle, a couple things I need to take note of. This point right here, let's call it P, has some x value and the y value of the sine of x because it's on my graph. Well, if this point right here is P, what can you tell me about this point right here? Well, we know that this value right in here is going to be the same as this value right in here. And so if we're calling this x, then this is x also. So this point then becomes pi minus x. So here's pi minus that x. And then my y value, of course, of sine of x. So with that being said, if we're actually trying to find the largest area possible, I need to figure out what the area of this rectangle is going to be. The height of my rectangle is sine of x. But what about our length? Well, our length is pi minus this part and minus this part. So pi minus 2x. That represents the width of our rectangle. So there's my area. I'm going to simplify that a little bit and then figure out where that is maximized by finding the derivative and the critical points. So this is the same thing as pi times the sine of x minus 2x times the sine of x. Now we're ready to take our derivative of that. So a prime, this is the derivative of that area of the rectangle function, is derivative of sine is cosine, so pi times the cosine of x, minus, here I have to use my product rule, so 2x times the derivative of sine, which is cosine of x. We should put a parenthesis or bracket right there, plus now the second term, sine of x, times the derivative of the first, which is just 2. And then I close that with my bracket. Simplifying that a little bit, I get pi times the cosine of x minus 2x cosine of x plus 2 times the sine of x. There's my derivative. So I want to find the critical points of that, and so I would just take my calculator, set it equal to 0, and find out what x equals. I'm going to push pause and do that. Alright, so these are what I got for my numbers. I got x equal to 0.71, and in this case it's obvious to us that we don't need to check our endpoints because 0 and pi are not going to give me optimal areas. So when x is 0.71, that's when my area of the rectangle is the largest. So what would that area be? It would be this number, 1.12. So what is the largest area of the rectangle you can have? To answer that question, I'd say it's 1.12 square units. And then it says what dimensions give that area, and so my length, which is sine of x, so sine of 0.71 is 1.72, and my width, which is pi minus 2x, is 0.65. Here it is written the book's language. Talk yourself through that if you need to. And you just answered your first optimization problem. Good work. We have several more we'll do. Maybe I'll just do 2 more on here, and then the others we'll wait and do together on Monday. I want to see you attempt as many as you have time to do. Looking at this one, it says find 2 positive numbers whose product is 750 and for which the sum of the one and 10 times the other is a minimum. Alright, so let's call our 2 numbers just x and y, and we know that x times y has to equal 750. And then we want the sum, which is a number we don't know, of x plus 10 times y to be a minimum. So if we want that to be a minimum, I need to change how I have this written. So I'll rewrite, oh, that maybe got cut off. Let me start over. So I'll rewrite that as x equals 750 over y, so that now I can use substitution to put that in for my x value right there. So s really is 750 over y plus 10y. And I want that equation to be minimized. So I take my derivative of that, and when I took that derivative, we have negative 750 y to the negative 2 plus 10. I set that derivative equal to 0, subtract 10, divide by negative 750, so I have 1 over y squared equals negative 10 over negative 750, so that'd be 1 over 75. You flip-flop them, so take reciprocals, y squared equals 75, and y equals plus or minus the square root of 75. But we were told originally that we had 2 positive numbers, so the negative is out, and y equals the square root of 75. And you're welcome to leave it like that, although we know that is also equal to 5 times the square root of 3. So that is what y equals. To find what what x equals, I'm just going to take that value and substitute it right back in here for what x equals, and 750 divided by 5 times the square root of 3 is 50. Let's see, x equals 50 over the square root of 3. So those are your 2 numbers. One thing that I didn't do here is to prove that that's a minimum value. I think in this example, probably the easiest way to show that that is a minimum is using the second derivative test. So how would I use my second derivative test to show you that? Let me erase a little bit here. So second derivative then would be 2 times 750 is at 1,500, y to the negative third, and then I'm evaluating my critical point at that number, so I put 5 times the square root of 3 into y. That gives me a positive number, and so when I evaluate this at y equal 5 square root of 3, my answer is positive. And if your second derivative is positive, remember that tells us we do have a minimum. So there we have our x, we have our y, and by the second derivative, we showed that it is indeed a minimum. I'm going to go ahead and stop there instead of doing one more example for fear of running out of time on YouTube. So hopefully we'll run through the rest on Monday, and you guys have a great weekend.